Hello, Professor. My name is He Shen. Today, I'm going to demonstrate my course project, applying graph algorithm to analyze small molecule structures. In this project, I took four algorithms: BFS, DFS, Kruskal's algorithm, Dijkstra's algorithm, and applied them to real chemical structures. All right, let's start with the project overview. In biochemistry, small molecules can be modeled as graphs. Atoms such as carbon, nitrogen, oxygen becomes the vertical, and the chemical bonds becomes the edges. If we assign a weight of 1 to a single bonds and 2 to double bonds, then we can get the weighted graph. Since my SID is end with A, so I'm going to analyze these two molecules. Molecule A has 15 atoms and molecule B has 13 atoms. In all algorithms, all neighbor visits follow the alphabetical order. And to process these molecules, I used Python library called RDKIT. It converts the text of a molecule into a graph structure. Each atom gets a label like carbon 0, nitrogen 2, oxygen 4. And here is the molecule A. The molecule has a benzene ring on the right side. It connects to a 5-member ring in the center. And this middle ring has 2 nitrogen, N2, N5, and 2 carbon to oxygen double bonds, O4 to C3 and O14 to C13. And here is molecule B. A central nitrogen atom N3 connects a benzene ring on the left and 2 carbon branches on the right. And now let's look at the algorithm results. BFS explore the graph layer by layer using a queue. Starting from C7, it visits all direct neighbors first and then their neighbors, and so on. Here is the visit order of molecule A and B using BFS. And next is DFS. DFS goes as deep as possible before backtracking. I implemented it recursively. Here is the visit order of molecule A and molecule B using DFS. It can clearly shows the difference between BFS and DFS. And BFS gives you a wide, shallow tree, while DFS gives you a narrow, deep tree. And both of them have the same time complexity. And next is Kruskal's algorithm for the minimum spanning tree. The idea is sort all edges by weight and keep adding the smallest edge that does not form a cycle. For molecule A, the MST has 14 edges and total weight of 16. For molecule B, the MST has 12 edges and total weight is 12. And finally is Dijkstra's algorithm, finding the shortest path from C0 to C7. For molecule A, the shortest distance is 5. For molecule B, the shortest distance is 6. And to summarize the algorithm complexity, BFS and DFS are linear in the size of the graphs, and Kruskal's algorithm is slightly more expensive due to sorting, and Dijkstra's algorithm sits in between. All algorithms successfully reveal the different structure of molecules. And to sum up, this object deepened my understanding of graph algorithm and showed me how the computer science tools can be contribute to biochemistry. And BFS gives a wide view of connectivity, while DFS gives a deep dive into paths. Kruskal's strategy is sort all edges by weight, and Dijkstra's process elegantly found the optical path. That's all for my presentation. Thank you for listening.